Hello everyone, I'm Gao Liang and I'm a PhD student at the National University of Defense Technology. The topic of my presentation is FIFL, a fair incentive mechanism for federated learning. My presentation will include 4 parts. First, the background and challenges. Second, the proposed mechanism. Third, experiments and results. And last, conclusions. Firstly, I would like to introduce the background. One rare and difficult challenge of AI lies in how people dealing with data. In order to be robust and performant, modern machine learning and deep learning models need to be learned from sufficient data. However, concern regarding user data privacy and data protection appear while centralizing data from multiple locations. Thus, federated learning becomes important. Federated learning is a machine learning framework that enables multiple devices to collaboratively train models while preserving their data privacy. In federated learning, works only upload the model parameters instead of the raw data. That is, data does not move, only algorithms travel. Federated learning is a scenario of crowdsourcing computing, where the task publishing needs to share profit with workers to utilize that data and computing resources. In a typical communalization scenario of federated learning, data owners get rewards for sharing the data resources and computing resources. However, if the rewards do not match the corresponding utilities and expenses, they would quit the current training or join a higher federation. To achieve fair incentive, we must currently access the utilities for workers. In addition, guiding against malicious workers is also essential because they may upload meaningless updates to get undeserving rewards and damage to the global model. Thus, a fair incentive mechanism that tolerates attack is a must-have. How to ensure fairness and reliability of the incentive mechanism under attacks is another challenge in federated learning. We show a case for federated learning. The training process can be broken down into 3 steps. Federated learning typically starts with a global model that acts as a baseline. In the first step, this global model is sent out to workers. These local copies are then trained on the local dataset by the workers, learning and improving their performance. In the second step, the workers will send the learned model parameters to workers. In the third step, the server aggregates the learned parameters when they receive them. Then the global model is updated and shared once more with workers. The entire process then repeats. The FIFL framework is shown in the figure. FIFL can be divided into 4 components: attack detection module, reputation module, contribution module, and incentive module. The attack detection module separates the attacks by checking the abnormal gradients and then filters them out. In the reputation module, we extend the subjective logic model with the time decay factor to calculate the work's reputation based on the historical updates. In the contribution module, we define work's contribution based on the similarity distance of work's log gradients to the global gradients to distinguish their utilities. In the incentive module, we use the products of work's contribution and reputation to decide the share of the rewards. The attack detection module aims to identify and eliminate attacks. Federated learning relies on the assumption that the averaging parameters of multiple log models yield a good estimator for the designed global model. The attacks had to upload gradients wholly different from the normal gradients to damage the global model. Thus, in the attack detection module of FIFL, we identify attacks through detecting the abnormal gradients. The reputation module measures the reliability of workers, which is defined as their probability to provide valuable gradients. In order to measure workers' reputation dynamically and objectively, we extend the subjective logic model with a time decay factor. Specifically, older events cry smaller rates, and the recent events are given large weights. The contribution module aims to measure the utility of workers. We calculate workers' contribution based on the distance between the local gradient and the global gradient. In FIFL, we calculate workers' rewards, considering both their contribution and reputation. The right figure shows the relationship of contribution, reputation, and rewards in FIFL. Contribution is the indicator to measure workers' utilities in each iteration. Reputation is the indicator that measures workers' reliability to produce useful gradients in a long time. In FIFL, the task publisher determines workers' rewards as the products of workers' contribution and reputation. Okay, now we move to the part of experiment. In the experiment, we set 3 types of workers in a federated learning system. Honest workers. Honest workers always calculate and upload gradients honestly. Sign flipping attacks. The sign flipping attacks flips the sign of low gradients and multiply a coefficient to undermine the global model. Data poison attacks. The data poison attacks train the network with a dataset in which part of labels are incorrect. In the experiment, we use the following baselines to evaluate the effectiveness of FIFL. In equal incentive, all participating workers get the same payoff. In the individual incentive, a worker's reward is proportional to its contribution while training independently. The union incentive sets the worker's profit as the marginal contribution, which is defined as the revenue the federation gained while the work joins. The Shapley incentive uses the average of all the marginal contributions to all possible collisions to determine workers' rewards. In a reliable scenario where all workers are honest, we first establish a federated learning system that contains 20 workers. The amount of training samples in the local dataset for each worker is randomly generated, which is uniformly distributed from 1 to 10,000. The left finger shows the reward distribution for workers with different qualities of training samples. The x-axis is the amount of training samples. The y-axis represents workers' rewards obtained from different incentive mechanisms. As the results show, the equal incentive rewards workers equally, and the FIFL spends the least on the low-quality workers and the most on high-quality workers. The right finger shows the system revenue of different incentive mechanisms. The FIFL achieves the highest system revenue compared with the baselines. In an unreliable scenario, there are attacks that try to damage the training process. The left finger shows the impact of attacks' evil intensity. The damage of attacks to the federated system increases as the evil intensity increases. The right finger shows the advantage of FIFL in unreliable scenarios. FIFL effectively improves the system revenue compared with the baselines. The reason is that the attack detection module of FIFL identifies and eliminates attacks. The other methods has no defense against attacks, leading to decline in the system revenue. Then we show the effectiveness of each module in FIFL. The above finger shows the effectiveness of the attack detection module. The x-axis is the communication iteration. The y-axis is the global model's test accuracy and loss. The results indicate that the attack detection module is useful to prevent attacks from damaging the global model. The model without the attack detection module crashed on the attacks, and the model with the attack detection module maintains high performance. Reputation indicates work's capability to produce useful updates. In the left finger, PA is the probability of a work honestly produce useful updates. We can observe that a work's reputation fluctuates around its probability to produce useful updates. The right finger shows the contribution of workers. PD indicates the error rate of labels in the worker's local data sets. The results show that as the mislabeled data increases, the contribution becomes smaller. Then we show the effectiveness of the incentive module. The left finger shows the reward of different works using FIFL mechanism. PD is the rate of works mislabeled data. We set PD equals 0.2 as the acceptable threshold. The right finger shows the FIFL fairly punishes same flipping attacks. PS is the attack intensity of same flipping attacks. From the results, we know that the rewards are positively related to works qualities. Now we come to the last part, conclusion. FIFL has 3 advantages. Attack resilience. FIFL works in unreliable scenarios as it prevents attacks with the attack detection module. Fairness. Combining with the reputation and contribution, the task published could fairly determine the rewards for workers and punish the attacks. High system revenue. FIFL achieves high system revenue than baselines in both reliable scenarios and unreliable scenarios. That's all for my presentation. If you have any questions, please feel free to contact me. Here's the email address. Thanks for your listening.